Ever wondered what it would be like to travel faster than the speed of light, to traverse the universe in the blink of an eye? Welcome to the fascinating world of quantum space travel, a realm where science fiction meets science fact. Here we explore theories that suggest we might one day be able to hop across galaxies as easily as crossing the street. One such theory involves wormholes, cosmic shortcuts that could potentially link two distant points in the universe. Then there are warp drives, theoretical engines that could allow us to surf the waves of space-time. And let's not forget tachyons, elusive particles that may travel faster than light itself. Each of these concepts presents a unique set of challenges, complexities, and profound possibilities. Today we embark on a journey to understand these complex concepts in a simple and engaging way. Let's start with wormholes, the cosmic shortcuts of the universe. These theoretical tunnels, as fascinating as they are elusive, are essentially solutions to Einstein's field equations. Picture space-time as a sheet of paper. Now, suppose you wanted to travel from one end to the other. You could trek across the entire sheet, or you could simply fold the paper, bringing the two distant points together, and voila! You have a shortcut. That, in essence, is a wormhole. But what makes wormholes truly intriguing is their inherent instability. Imagine trying to balance a pencil on its tip during a hurricane. That's what it's like trying to keep a wormhole open. They are incredibly sensitive to disturbances and have a propensity to collapse under their own gravity. This means that any attempt to traverse a wormhole could potentially lead to its collapse, squishing anything inside it into oblivion. Not exactly a pleasant journey, is it? Furthermore, stabilizing a wormhole is no easy task. Theoretical physicists suggest that we would need something known as exotic matter, a type of matter with negative energy density, to keep a wormhole open. But here's the catch. We're not even sure if such matter exists. And even if it does, how do we harness it? Despite these challenges, the potential rewards of mastering wormhole travel are immense. Imagine being able to traverse billions of light years in the blink of an eye, visiting distant galaxies that would otherwise remain forever out of reach. The possibilities are quite literally astronomical. So wormholes could potentially allow us to take shortcuts through space and time if we can figure out how to stabilize them. It's a big if. But then again, quantum space travel is all about dreaming big and pushing the boundaries of what's possible. After all, who knows what secrets the universe has in store for us? Next on our list are warp drives, the real-life inspirations behind many sci-fi stories. These engines of science fiction, so vividly depicted in our favorite space operas, are not just figments of creative minds. They are serious contenders in our quest to conquer cosmic distances. Imagine you're a surfer, but instead of riding the turquoise waves of the Pacific, you're surfing the cosmic waves of space-time. That's the essence of a warp drive. It's a propulsion system that manipulates the fabric of space-time itself, compressing the space in front of it and expanding the space behind it. It's like creating a wave in the cosmic ocean, which your spaceship can ride, effectively moving faster than light without breaking any of physics' sacred speed limits. But just like with any high-speed pursuit, there's a catch. To create this space-time wave, we'd require something called exotic matter, a type of matter with negative energy density. Now, you might be wondering, what on earth is negative energy density? Well, it's just like it sounds. It's energy that's less than nothing. It's the kind of stuff that makes your head spin, but it's essential for a warp drive to function. You see, this exotic matter would be used to keep the warp bubble stable, to stop it from collapsing in on itself and taking our spaceship with it. It's a bit like inflating a balloon and needing to keep pumping air into it to keep it from deflating. So, where do we find this exotic matter? That's the million-dollar question. As of now, it's purely theoretical. We have no idea where to find it or even how to create it. But who knows what the future holds? Our understanding of the universe is constantly evolving, and with it, our technological capabilities. So, warp drives might allow us to surf the waves of space-time if we can find or create the right kind of fuel. It's a tantalizing prospect, one that keeps us looking up at the stars with wonder and anticipation. Now let's talk about tachyons, the rebels of the universe that defy Einstein's speed limit. You see, tachyons are theoretical particles that exist only in the realm of theory and speculation. These little mavericks are believed to travel faster than light, flouting one of the most fundamental laws of physics. Nothing can surpass the speed of light. Tachyons are enigmatic, to say the least. They exist outside the boundaries of normal physics. They're a bit like the outlaws of the particle world, always on the run, always ahead of the law, in this case the law of light speed. And this speed, this breakneck pace at which they supposedly zip through the universe, gives them a rather unique property. You see, if tachyons do exist and they do travel faster than light, then they could potentially move backwards in time. Yes, you heard that right, backwards in time. A world with tachyons is a world where the future can influence the past, where cause doesn't necessarily come before effect. Bizarre, isn't it? But with these exciting prospects comes some serious potential problems. If tachyons can travel back in time, we run into all sorts of paradoxes. What if you send a message to your past self, warning them of a future event? That could change the course of history, and not necessarily in a good way. This is known as a causality paradox, and it's something that physicists and philosophers have been wrestling with for years. So, tachyons could potentially allow us to travel faster than light if we can find them and figure out how to use them without causing paradoxes. But for now, they remain elusive, a tantalizing possibility on the fringes of our understanding. They're the rebels of relativity, the outlaws of the universe, always one step ahead of us. But who knows? Perhaps one day we'll catch up with them. But of course, none of this is as simple as it sounds. Quantum space travel, while tantalizing, is a complex labyrinth of challenges that scientists are still trying to navigate. Let's start with wormholes. These cosmic shortcuts may seem like the perfect solution for interstellar travel, but they're far from stable. Imagine trying to balance a pencil on its tip during a hurricane. That's the level of instability we're talking about. Wormholes are prone to collapse under their own gravity. That's like having a tunnel cave in on itself just as you're about to walk through. Not the most ideal form of travel, is it? Then we have warp drives, surfing the cosmic waves at speeds that could potentially surpass light. However, they come with their own baggage. The concept requires exotic matter with negative energy density to function. And where can we find this cosmic fuel? That's still a question we're grappling with. And let's not forget tachyons, those elusive particles that thumb their noses at Einstein's speed limit. The problem with tachyons is just that, they're elusive. We've yet to observe these particles directly, and even if we could, their propensity to mess with causality could lead to some rather confusing timelines. Imagine traveling faster than light only to arrive before you left. That's a paradox that could give even the most seasoned time traveler a headache, but it's not all doom and gloom. Each of these challenges presents an opportunity for discovery, a chance to push the boundaries of our understanding. The instability of wormholes could teach us more about gravity. The quest for exotic matter might lead to new insights into the nature of the universe. And the elusive nature of tachyons could force us to rethink our understanding of time and causality. The journey to faster-than-light travel is fraught with challenges, but it's a journey we're excited to undertake. After all, every great adventure comes with its share of hurdles, and the prospect of quantum space travel is no different. It's a cosmic puzzle waiting to be solved, a mystery that beckons us towards the stars. And it's not just about the physics. There are also ethical questions to consider. When we think about quantum space travel, we often get lost in the dazzling world of wormholes, warp drives, and tachyons. But what about the ethical quandaries that come with these theoretical journeys? Imagine for a moment that you're able to traverse the cosmos at speeds faster than light. You're not just a traveler, but a time traveler, able to visit your past and perhaps alter your future. What happens if you run into your younger self? Would you give advice, warn about upcoming challenges, or just sit back and watch the past unfold, knowing you have the power to change it? This is the paradox of time travel, the ethical dilemma it presents. The potential to rewrite history is a tremendous responsibility. Every action, every word could ripple through time, altering the course of events in unforeseen ways. This isn't just theoretical physics. It's a question of right and wrong, a question of power and how we choose to wield it. Moreover, consider the impact on the societies we might encounter. If we have the ability to reach distant civilizations, what right do we have to interfere? Could we become cosmic colonizers, imposing our values on alien cultures? Or would we be humble explorers, respecting the autonomy and sovereignty of the civilizations we encounter? And what about the cost of these journeys? The resources required to build a warp drive or stabilize a wormhole could be astronomical. Who decides how those resources are allocated? Who benefits from these expeditions and who bears the cost? These aren't just hypothetical questions. As we push the boundaries of what's possible, we also push the boundaries of what's right. The frontier of space is also the frontier of ethics. We must navigate both with care and consideration. So, quantum space travel isn't just a theoretical challenge, it's also an ethical one. As we look to the stars, let's remember to look inward as well. Our journey is not just across the cosmos, but through the complex landscape of ethics and responsibility. As we stand on the precipice of this new frontier, we have to ask ourselves, should we chase the stars, even if they're light years away? The universe is a treasure trove of mysteries, and we've just scratched the surface. Wormholes, cosmic shortcuts through space-time are tantalizing prospects. Warp drives capable of compressing and expanding space could potentially make faster-than-light travel a reality. Tachyons, the rebels of relativity, defy Einstein's speed limit and offer a wild ride through time, but these concepts are not without their challenges. The instability of wormholes, the elusive nature of exotic matter for warp drives, and the causality issues with tachyons present significant hurdles. And let's not forget the ethical dilemmas that quantum travel could pose. As we delve deeper into the cosmos, let's ponder these concepts, question the possibilities, and embrace the unknown. Join us on our next theoretical journey as we continue to explore the fascinating world of quantum space travel.